and Thomas, are you both like direct colleagues at Lightning or?
I mean, Lightning is not that large, right? It's like 50 people. Obviously, not all of them are engineers, and so I basically know most of what I know about profiling from Taylor, which means that I didn't know that much before Taylor talked to me.
I guess that just means I did a bad job documenting and evangelizing when I was still at Meta.
It's okay, and now you're paying for it with more meetings, so it works out. So you still have skin in the game, so it's fine.
Yeah. And obviously, I mean, I saw Taylor doing internal presentations at Lightning, and so I immediately say, well, yeah, wouldn't this be something for the CUDA mode? And so this is essentially how it came about too.
Yeah, cool. I think we are ready to start. Hello, everyone. Thanks for tuning in to our 16th CUDA mode lecture here on the CUDA mode Discord server. Today we have a special guest, Taylor Roby, who's working at Lightning AI and an expert in profiling, and he will talk today about profiling, I guess, like also PyTorch. I also heard in advance that he will do a really hands-on interactive session. So no prepared slides, but really looking into the code and profiling actual model, I guess. Yeah, so just as a quick reminder before we start, we do this normally for 1 hour. Please use the chat which comes with the stage channel to ask questions, and we will try to forward them to Taylor if this is possible. And Taylor, if you are ready, would be great if you could do a quick introduction about yourself in the beginning, and the stage is yours.
Hi, so I'm Taylor. I'm an engineer at Lightning. Before I was at Lightning, I was on the PyTorch team doing various profiling and runtime optimization stuff. And my background has traditionally been in profiling, benchmarking, and model optimization. So what I thought I would do today is rather than come up with a bunch of prescriptive slides, just pick a model, start poking it with various profilers, show how the various tools interact and what the trade-offs are when using them, and then just kind of go through the process interactively of optimizing a model. What that means is that feel free to jump in at any time if you have questions about what you're seeing, if you have sort of hypotheses. Again, this is meant to be a very interactive session. So to start off with, for those of you who don't know, Lightning has a product called Studios, which is an interactive collaboration environment for coding, and particularly with an ML focus. And so what I did is one of the features that Lightning has, these studios, are that you can publish a self-contained set of code and then duplicate it and run it on your own cloud hardware. And so what I've done is I've gone and I've picked, one of my colleagues has published this studio on how to fine tune the Gemma model. And so I've duplicated it, and then we're going to run through it and then sort of see where the gaps are and how we can build them up. So the first thing that we're going to do is just sanity check that we can run it, that it's using the GPU, etc. So we run this code, and if we go over to our GPU metrics, this is essentially NVIDIA SMI with a nice GUI in front of it. What you can see is that it will use about 80% of the GPU. Now, it's worth noting here that in this case, again, this is NVIDIA SMI utilization. So it just means that something is doing something on the GPU. But we need to dive deeper to know if it's actually sort of making sensible use of the card. So if we go ahead and cancel this, the first tool that we can turn to is one that I imagine this group will be quite familiar with. I know a number of previous lecturers have used it, which is Nsci Systems. So if we run this command, I ran it just a little bit earlier, so I'm just going to jump directly into the trace. What we can see here is, first, there's a lot of startup time where we're not really doing anything. This is pretty normal, and we really only care about the steady state. And then to make things a little bit easier, I've gone and I've added NVTX markers so that we can at least have some idea of where these kernels correspond to our code. So what you can see is the first iteration is much longer than the others. This, again, is very common because the system is warming up, caches are being initialized, pools are being created, that sort of thing. And then as we go on, we get to closer to a steady state. The other thing that we'll notice as we look at this is it's not a particularly inspiring picture right out of the gate. Namely, if we look at our warp occupancy, then what we can see is, yes, we're doing stuff, but we're not making particularly good use of the hardware. But it's also, in this configuration, somewhat hard to drill down into why this is happening, because if we go to the CUDA kernels and what's actually being run and zoom way in, we'll see things like Cutlass. Okay, so there's a gem in there somewhere. We can see gem here. If we zoom in, we'll see, okay, some flash backward, but it's very difficult to go from this kind of view to something prescriptive of what should you actually be doing to optimize your model. So there's another tool in PyTorch, which is the PyTorch profiler. And I've done a little bit of instrumentation ahead of time to call this in a somewhat sensible way. So the API here is that with Torch profiler profile, and then you run your code, and inside the code, I have it so that it's going to stop after a couple iterations, because all of these profiling systems are collecting a huge amount of information, and as a result, if we collect more than a couple steps, we'll essentially have too much and the entire system will keel over. So we're really just grabbing a small snapshot and trying to extrapolate out from that. So if we go ahead and run this, and let's give it a moment to run.
You can always share fun anecdotes like while this stuff is running.
Yeah, so I think one of the things that was kind of interesting is as I was putting together this talk, it really went in a very different direction than I expected. So I expected it to be a principally kernels talk, and some of the initial stuff that we'll see really seemed to be going in that direction, and then it really skewed into a systems talk. And speak of the devil. All right, so the principal artifact that you get out of the PyTorch profiler is a Chrome trace. And the way that you read this Chrome trace is time is on the x-axis, and then it's an icicle plot showing stacks. So let's ignore this part for a moment, and then, and this is unrelated, this is instrumentation, and then let's just go into the stream. So this looks very much like what you would recognize from NSYS. You've got CUDA kernels, and then they're in sequence. Now, it's worth noting this is less detailed than when you would get out of Nsight Systems. This is mostly just showing you the time of the kernels. And there are some statistics around the grid and the block, but again, it's much less detailed. But the trade-off you get here is that this is aware of the PyTorch runtime. So if we select a kernel, then what we can see here is we can walk up to the source code. So what you can see here is that we can walk up to the matrix multiplication and the linear, and we can walk all the way up to where in the code this came from. And this is somewhat useful because when we're looking for gaps in the profile, we can see, okay, this is a gap somewhere around the RMS norm layer, right? Because I see before here and then after. So kind of ipso facto, this gap has to be coming from RMS norm. And then we can just, typically the way that you go about optimizing these is you just kind of scan around and you look for gaps, and then you try and build a narrative around why these gaps would be there. One thing that I wanted to point out as the sort of analog here and why it's very important to get into steady state is you can see you have this initial regime, which is the first step, which looks very different from the much more regular structure of the second step. The other kind of pattern that I want to point out that you can use to kind of at a glance figure out what's going on is the forward pass is your Python code. And so when you see these deep stacks of source code, this tells you that you're in your Python. At some point, you're going to call backward, and it's going to switch the C++ of the Autograd engine. And the way that's going to manifest is you're going to block in your thread, and then you're going to switch over and start dispatching work in C++ on a separate thread. And so this is just a very easy and convenient way to differentiate between the forward and the backward path. So we don't want to look at this because, again, this is not going to be particularly representative. So instead, what we want to do is we want to zoom in on the CUDA stream, and what you can see as you zoom in is that the somewhat regular pattern starts to emerge, where you have a couple of these gems that are sort of big and bulky and saturating the stream, and then you have the clusters of kernels. And if we zoom in on what they're coming from, they are these element-wise. And if you were in Nsight Systems, then what you would see are things like index element-wise kernel. What's nice about going from this direction is that you can then map those back to something sort of in your source code that you can work with. And in particular, if we zoom around, I think it was here. What we'll notice, yeah. So actually, the first thing that I'll point out is that there's almost no difference between the launch time and the execution time, right? In a well-behaved CUDA system, then you would launch this and then you'd have a full work queue, and much later the kernel would actually be run. So instead, what's happening is we're launching it. This kernel actually has some work, but then it runs out of work and is waiting for the next host kernel. So if we look,
so Taylor, sorry to interrupt you. There's already a bunch of good questions, so maybe let me just go through them.
Okay.
So Eric is asking, should we think of the icicle plot as being local to one SM or spread across all SMs? Do we expect all SMs to be running the same kernel at the same time?
Good question. So it is not local to one SM, and in fact, if you were using multiple streams, then you could have multiple kernels overlapped, and the CUDA hardware scheduler is going to try and allocate SMs to these kernels as they are available. So no, it's a many-to-many relationship.
Right. And then the second question, and I apologize, it's an acrylic name, so I don't know how to read it. But they're asking, like, can you convert these stack traces to a flame graph?
Yes, so you actually can. Why don't I just go ahead and segue? So one of the things that initially prompted, and this is not exactly a flame graph, but you'll see in a moment why, how it relates. So one of the things that initially prompted this talk is I've been doing some work to try and integrate the PyTorch profiler into the Lightning platform and try and make some of this easier. And one of the things that you can do when you sort of own the system end to end is that you can start to do tweaks to the environment that enable cool things. So in this case, what we can do is we can start to instrument the processes themselves so that when they're triggered, they will collect a profile. So this is going to take a second to run and then post-process, but when we come back, I'll be able to show some of the initial aggregation that is sort of analogous to FlameGraph, and FlameGraph is planned for this. Essentially, you could turn this into a FlameGraph by doing a summation over all of these icicles.
So Ayush is now asking another question, which is, like, I'm gonna rephrase the question slightly, but like, can you generally figure out like differences in GPU architectures? Like, do different GPU architectures, would they end up having like slightly different traces?
You mean like Volta, Ampere, Hopper, etc.?
Sure. Yeah.
Yeah, so there are a couple of things that that will immediately jump out at you. So the first one is pretty much all of the gem kernels will be prefixed by the architecture of the kernel that they're optimized for. But the other thing that is a little bit more, and some of them you'll see will be very characteristic. So for instance, like if you see a TF32 map model, that has to be Ampere or later. But you'll notice, so I'm running this on an L4. I have the L4 datasheet handy. And later in the talk, what we're going to do is we're going to start comparing the kernels that we see here to what we see the data sheet is predicting for various things. And what you'll see is that there's essentially a very strong correspondence. So the architecture will generally determine what is the limiting factor for these different steps.
Excellent. Yeah. Thank you, Taylor. Back to the talk.
Excellent. And yeah, so by the way, you can see this has completed. You can see it happened to capture a very sparse region. And if I scroll down, sort of what I'm working on is doing aggregation of kernels to source code so that you can say, okay, within this, all right, I'm spending a bunch of time in this particular linear layer. So rather than having to sort of squint at the Chrome trace and say, roughly visually where is it? No, you can come over to here and say, okay, these are the parts of my code that are hot.
This is pretty sick, actually. I think that there's someone in chat who agreed. There's two people, Jonah Turner and Evelyn Mitchell, both agreeing that this is awesome. I remember Scalene had a similar UI that I thought was really sick. So it's like really nice to see this like in an end-to-end system. I guess though, like the fact that A10 linear is slow, is it like how actionable is that? Like that one's a bit trickier, right? Because like it doesn't necessarily jump out as to anything that you might want to do with that quite yet.
Sorry, could you repeat the question?
Like the fact here that it's a linear layer that's slow is not like particularly actionable because like a lot of the sort of common optimization techniques that we might use, like fusions, don't really apply here. So yeah, is it? Yeah. So unless there's another one you're thinking of.
Yeah. So I'm actually going to kind of slightly skip ahead because I do think that this is a very important question of you see a gem, and this is kind of the same thing that I was saying, when we got here, which is, all right, I see a gem, I'm saturating my stream on a gem, so life must be good, right? But if we actually take this and we follow it back to an example here, I'm going to pick this one here. So if we look at so this kernel took about 300 microseconds. And from here, what we can do is we can say, all right, let's look at the shape of this. So one of the nice things about the profiler is that it captures these shapes. So 61 by 2048 by 16384. So if we do a little bit of back of the envelope math, then what you can see here, Python, so 61 times 2048 times, right? This is the cubic of a matrix multiplication. You're doing two operations. You're doing a multiply and an add, and then divide this by 1e12 for teraflops. And then the other thing is that from a datasheet perspective, so this is sparse, but cut this in half and you get 121 teraflops is the datasheet flops for an L4, so 121 teraflops. And then multiply this by 10 to the 6 to convert that into microseconds. And if my math is right, this predicts that this matmul, if you were sort of hitting the datasheet flops, should take 33 microseconds. Instead, we come over here and we see that it's taking 10 times that, which is a little bit interesting. But on the other hand, if we look at this slightly differently, right? If we say 61 times 2048 plus 2048 times 16384, right? So we look at what it takes to round trip the weights through memory. They're bfloat 16, so there are 2 bytes per weight, and then divide this by 1e9, and then the datasheet flop or the datasheet memory bandwidth for an L4 is 300 gigabytes per second times 1e6. Well, now this is predicting that it should take about 225 microseconds. Add a little bit of overhead, you're never going to achieve sort of true peak. And this tells you that even though this is a gem, it's a bandwidth-bound gem, not a compute-bound gem. And if we sort of look at the shapes, then this makes a degree of sense. It's completely dominated by the weight, the weight of this linear layer. The actual activation, if we go up a level, you can see that this is batch size 1. So the actual activation is tiny. And so you're bringing the entire weight into the SM memory only to use a tiny amount of activation and then send it back. So yeah, even just identifying that this is sort of, you are spending your time here and you should investigate it, you might come to the conclusion that yes, this is a gem. It is sort of, my model is doing what it's supposed to be doing. It is supposed to be spending its work there, but it might tell you, hey, I'm spending a bunch of time there and it's optimizable. Any other questions?
Like I'll ask one, like just like because I think this is like this has been a pretty fun digression. So like considering that it's like memory bandwidth, like I think you mentioned that this is like, I think like a LoRa-like model. So here is like an area where I would expect like a conversion to like a smaller D type might be very beneficial, like, you know, potentially like using int4 or something like that to optimize this part. So I'm curious, like basically here, you know, we know it's a memory bandwidth bound matmul, and so like, is your head going towards like, hey, should we fuse something, or are you going towards like, let's just make the D type smaller?
Yeah, so I tend not to jump to let's make the D type smaller just because that is not a semantics preserving change. And so when possible, I try to get as far as I can while preserving the original computation because I don't know what, say, quantization is going to do to my accuracy. And then sort of once I've exhausted the rest of that, yes, then I can turn to those more destructive techniques. But it's interesting that you mentioned fusion because that's actually where I was going next. So if we come over and we look at specifically this regime and we zoom in, what we see is element-wise, memcopy, yeah, vectorized element-wise. So we come here and we see this enormous kind of chasm of vacancy and element-wise operation. And we're sort of trained to think, okay, what this is demanding is fusion. If I only launched one kernel to do all of this at once, then everything would be great. I wouldn't have this gap. And so I picked just a sub task, which is the supply rope task. If we go over to the actual, I've pulled it into a side benchmark, and we'll run through a micro benchmark. What you can see is it's essentially some copies, a little bit of concatenation and math, and then conversion. So this seems like an extremely fusible operation. So let's go ahead and kill this here. And then run the supply rope benchmark. And what you see is that this takes about 50 microseconds. So, okay, cool. We know how to write fast kernels, or at the very least, we know people who do. So I borrowed from Tom, who in turn borrowed from Unsloth, this fast embedding kernel. So great, I have a fast embedding kernel. Let's run it. I'm going to not run this quite yet for reasons that you'll see. So this is our baseline. Our fast kernel is twice as slow, which is a bit surprising. But if we crack this open in the profiler, then it actually starts to make a lot more sense. So let's go ahead and grab this trace. I'm going to open a new Chrome trace tab. And what you can see is, let's ignore all of this because we're interested in the steady state. We have a bunch of clever machinery, right? We have binding, we have cache keys, we have all sorts of clever things. And what does this do? Well, at the end of the day, it generates a really awesome kernel, right? This 2 microsecond kernel. But that's not our problem, because our problem is we are doing too much work on the host for the amount of work that we're doing on the device. And so doing more work on the host to have a better device characteristic is actually going in the wrong direction. And so without ever integrating this in the model, I can tell this is not going to help me. So fundamentally, what both of these are crying out for is more batch size. Because what your batch size does is it increases the amount of work that your kernels are doing and it does not increase the amount of time that you're spending on dispatching them to the host. It is also the case that if we look at specifically these map malls, increasing our batch size is going to increase the amount that we have to load on the smaller tensor. And right now, these tensors, these activation tensors, are so negligible compared to loading the weight tensors that is essentially free to increase the batch size on these tensors. So let's go ahead and do that. So if we come over to here, and I believe it is micro batch size 2.
And Taylor, what would be the optimal CPU utilization, if you like, say in this like host versus device scenarios? Is this because I've seen a lot of situations where CPU was at 100%, but I wasn't sure is this like something which is also caused by, I don't know, like waiting operations, or if isn't it under optimal circumstances, is it just it should be like not 100% CPU utilization?
Yeah, so generally, for the model side, your CPU utilization should be nearly zero because you just have a single thread and it's dispatching kernels. And maybe it's doing some more clever things in these modern systems, like it's JIT compiling a kernel or something like that. But really fundamentally, it's a single threaded task. When you have high CPU utilization, it is almost always because your data loaders are highly parallel and they're doing lots of transformations to prepare the data. And so I would say if you have very high CPU utilization, but your data loaders are fast enough, that's great. But you shouldn't really shoot for high utilization on the CPU the same way that we shoot for high utilization on the GPU.
All right. So, but if you mean like jitting and stuff, this should normally only happen during like the first runs of kernels, right? If this is, or maybe if there are different shapes or so. This is a different question. For example, during inference,
Yeah.
like, do you there aim for like some set of different of shapes which are fixed basically, and then you know what is going into the system, and it's not like completely dynamic.
Yeah, as a general rule, you need to run a kernel thousands or tens of thousands of times in order to properly amortize the cost of computation or of compilation. And so what we generally find is that we do want to run in a system where we have static shapes, or if we can't have static shapes, then we want a compiler which is somewhat resilient to dynamic shapes. And I think we've seen an increase in the prevalence of dynamic shape compilers recently. So one of the things that the PyTorch profiler can do that I'm collecting automatically is it can collect memory traces. Actually, to understand why this is important, let me run one more command, which is I'm going to, all right, so batch size 2 is great. By the way, if we look at the actual statistics, what we'll see is I'm getting just under 8 batches per second. I was getting 12 at batch size 1. So I'm not twice as slow, but I do have twice the batch size. So I'd like to continue this trend, but I can't because if I go up to batch size 4, I run out of memory. So let's go ahead and grab this timeline. Download. Here we go, to see why. And what we see is a little bit surprising. So first of all, just to interpret this timeline, the green is your weights. And so this is very common. You have this static allocated buffer of weights at the bottom. In this case, it's about a 3 billion parameter model, FBF16 weights, so just under 3 gigabytes is expected. In our activations, we have our forward pass where we build up our activations. They're decreased in the backward pass. Because we're doing LoRa, unlike normal training where we'd have these huge gradients for the weights, we just have these tiny, tiny gradients for the LoRa parameters. But what you'll notice here is naively, this seems like we should be able to go way up in batch size. This is a 24 gigabyte card. Batch size 2 is using about 1 gigabyte of activations. And yet, if we look at the maximum memory, what we'll see is that we're hitting up to like 18 gigabytes of memory, which means that there's something anomalous happening somewhere in the system other than steady state. And so there's another really nice tool in PyTorch to analyze this, and it is here. So profile only memory. And I'll show you what this is doing in a second. So fundamentally what we're doing is we're calling this API. So there's an always-on memory profiler that you can set in PyTorch, which is much lighter weight than the standard PyTorch profiler. But what you get for having that lightweight and giving up a bunch of information is that you get to run it for much longer than you otherwise would be able to. So here you can see I just ran it for the first 5 steps. And if we come over here and grab this, download it, and then there's a very nice visualization site that PyTorch provides that we can just drop this in here. And what you can see here is that something is off with our first batch. These kind of look normal. You have increase, decrease, increase, decrease. But over here, our first batch is enormous. It's consuming a ton of memory. And when I first looked at this, what I thought was, oh, I'm doing some kind of initialization or copy, or there's some kind of huge weight, huge thing that's special to the first step that's happening in the background. And I should go and try and diagnose it. But it turns out that this is actually not the case. If we come back to this Chrome trace, one of the nice things about having these is that you can very quickly kind of estimate properties of your model. And so if we come over to the embedding here, specifically this embedding op, not this one. Sorry about this. All right. I'm not able to find it, but just in the interest of time, if you scan around and you specifically look at the inputs to all of the models, then what you'll find is that we legitimately do have, where did you go? We legitimately do have a variable batch size. So typical sequence length for one of our training examples is something like 100, 200, but they go all the way up to about 1,000. And so when you hit one of these rare long sequence lengths, the entire system gets really, really big. You're forced to hold all of those enormous activations in memory, and this prevents you from batching the way that you would like to under normal circumstances. So if we go back, just make sure that I stay on track. I do want to make one point about this plot, which is, if we look here, let me zoom in a little bit, these look kind of normal. You have an increase and then a decrease, which again, very clearly and characteristically corresponds to you build up your activations in the forward pass, you free them in the backward pass. And even in this somewhat misbehaved example, you still obey that property. You build them up in the forward pass and you free them in the backward pass, except this is very characteristically building up in the forward pass, and then you have this cliff where you drop and then continue with the backward pass. So what's going on here? Well, if we, one of the nice things about this tool is that it captures source location as well as just the raw values and their lifespan. And if we walk through these source locations, eventually where this will take us is back to the LoRa file and specifically cross entropy. So there's this chunked cross entropy function, which I'll talk about in a moment, but essentially these are the chunks of the cross entropy. So one of the things about Gemma that is kind of interesting is that it has an enormous vocabulary size. Well, how this relates to memory is that your cross entropy is, right, its decision dimension is your vocabulary size. So if you have an enormous vocabulary, it means you have an enormous logits tensor. And in fact, this is why we break it up to not have so many enormous intermediates to try and bring down the peak memory. But if we look here, what happens? Well, we define this logits, which is, or we define this logits here, which is a list of really quite large tensors. And then we continue, we loop back around. And then here, we finally override logits. So this is why we're seeing this property here, is it's because it's not until the end of the forward pass of the next step that the Python reference to this is deleted. Because as far as PyTorch is concerned, it has no idea if you're going to try and access this in the future. And so if we manually delete the logits and repeat this exercise, essentially freeing that Python reference, which will be the last Python reference. And then we wait for this to collect the profile. Right, grab this. Now you can see that this sort of enormous persistent logits tensor is gone. Now, in this case, it doesn't really help us because our peak memory occurs before that. But I just wanted to point that out as when you see these like strangely uncharacteristic shapes in these profiles, it's often a good indication that something else is going wrong. On the topic of
so Taylor, like here, maybe you mentioned it already, but I was wondering if you could elaborate. Like how come the garbage collector couldn't figure out how to deal with the logits with logits and delete it automatically?
Yeah. So if we don't have this, it is legal Python, say here, actually, right, to say something like print logits. And we can do this because the variable is live, which means it holds a reference to the underlying tensor. So as long as the reference count is positive, we can't free this logit. We can't free this Python object, and the Python object is what's keeping the tensor memory live. So by explicitly adding this del statement, it also means that print, right? It's essentially a promise that I'm not going to do this in the future.
Oh, I see. Interesting. So like it's not about like, are you like, do you not need logits? It's like, are you allowed to use logits?
Yeah, exactly.
Oh, I see. Got it. Thank you.
Yep. So another thing that as we dig into this, you can see that this here.
So sorry. So Peter has asked the same question twice, so I owe him that. So Peter's asking, like, the with torch compile figure these kinds of things out. I think he had a question one for the fusions, and I think he might also be talking about the reference count problem here as well. And he's specifically, I guess someone else is saying, Eric is saying, only if you compile forward and backwards jointly. Actually, sorry, that's unrelated. So maybe just comment about torch compile here briefly.
Yeah, I think what I would say is that, yes, ideally an optimal, compiling system should be able to figure this out. But something that I think is very subtle here is that it is really hard to track down in Python where this is actually going, right? So for instance, if I do, right, this is legal. I don't even have to use F. I just have to have F, and it's going to capture logits, and right, there's this whole chain, right? It's very, very hard to prove things about Python programs. right? I don't know if Torch Compile even cares about supporting this, but I can say, you know, right? I can do this kind of, right? I can do terrible, terrible things in Python. So I would generally say, don't count on the compiler to be, extraordinarily clever. You should just do the extremely simple thing.
So, so Eric just elaborated on his point. So Eric is saying, if Torch compile only compiles the forward pass, the output of your function are the logits. So you don't know what happens with them. But if you do the
Yeah.
forward and the backwards together and compile, the compiler can know that you're never going to use logits again, and that they're not going to get returned from the function.
Yes, assuming that no other Python references occur. I mean, again, I haven't tested this. It would be great if Torch Compile can figure this out. I just don't know. I haven't tested it. But what I will say is, this is a very simple example where you could potentially figure this out. But probably the most common place this manifests, other than just in a bare scope, is that you attach it as an attribute of a function. Right, so you're reusing a tensor, and so you say, oh, I'll just put self._x equals blah, and then you use it a bunch of places in your forward function, and you're perfectly happy. You have to reuse that intermediate value the way you wanted to, but then you move on, and now this model has escaped the scope of whatever compilation you're doing. Right, there's no way to see where this is going, and it holds a reference to that tensor, so no compiler in the world can figure that out. Cool. Any other questions on this point?
No, I think you can keep going.
Okay. So something that I noticed that was kind of interesting, as I was looking through this chunked cross entropy, because it's where our peak memory occurs, is that if we so let's just find one and zoom in on it. Yeah. Okay. So I was going through here, and something that I noticed is there was a CUDA stream synchronize. And pretty much whenever you see any kind of host device synchronization, giant alarms should be going off in your head. Because sure, there is data dependent control flow, but it is extraordinarily rare. And so pretty much every time you see one, it's worth investigating. Now, if we go to the actual definition here, and this is one of the reasons why it's really nice to have this Python source location, is we can see it comes from this max function. So let's just open up Python and see essentially what happens when we do this. I'm just going to say x import torch. Right, and then max of 1, x. Cool, I get a value, but what specifically is this?
Yeah, so
right?
it's not a tensor anymore, is your point.
Yeah,
Right?
yeah. I think we have this like intuition when we write these that it's really this, and it's not. And so by punting this into a Python value and then doing math on the Python value, you are essentially forcing PyTorch to round trip this value. In this case, it's just we're chunking something out, and so we have to make sure that we don't divide by 0 in a chunk, right? Because the numerator will be 0, but we just have to make sure the denominator is not 0 in that kind of corner case. So on the other hand, if we do something like this, right, instead of max this, right, we do dot max torch dot ones like x. Now this is great, right? There's, as far as PyTorch is concerned, there's no as far as Python torch is concerned, there's no Python here except for the scalars in the arguments to ones, which we know how to deal with. And there's one other place where this shows up that I'll just kind of briefly jump to, just in the interest of time, which is, and again, the way that, we don't get here magically, we search, synchronize and find the places where it occurs. The other place that it crops up, I believe, is in LoRa.
Yeah, like the Scuda sync has bit me in the past. Like whenever you have like dot item calls as well in your code, like this shows up a lot.
Yeah.
So yeah, I couldn't agree more. This is like a really critical thing to avoid in your code.
Yeah. All right. So it looks like I am going to be forced. Oh, it might just be here. No, this isn't cross entropy loss. Okay, here it is. So you have a ton of them, an absolute ton of them in ZeroPad. So what's going on here? So let's go find ZeroPad. So where they're coming from, again, one of these things that you should always just be extremely wary of is torch.tensor, right? It's so convenient. You give it anything and it turns it into a tensor and it's great. But the problem is, so in this case, this is a list. In this case, the problem is it's a list, it's Python, it's on the host. And so in order to use this, it needs to send this to the GPU. And so it needs to stop, do the Python conversion, do the host device, right? The whole thing. Now, if we look through here, what we realize is this is actually static. It's set up once in init, and then you're done. You never actually modify it again. So we can replace it with this formulation, and essentially I'm just doing this but lazily. Because again, I threw this together in like 5 minutes, and in steady state, it'll be fine. We don't really care. Yeah, so just convert it to a tensor, put it on the device, and then leave it there. And now we can just call this directly. And between these two changes, it occurs one more time down here. If we now rerun our profile over here and grab our, now I'm just going to grab this one. It doesn't have the batch size, but we're just trying to get some profile out of it. Then what we're going to find is that the only time we do synchronize is when we get the loss to log. We go from like 1,000 synchronizations down to like 1 per step. So it's like or 2 orders of magnitude decrease. The other thing that does for us is when we're in these regimes, right? The reason that we got into this state in the first place is because sometime back here, we had gems, we had big amounts of work to let the host run ahead of the device, but then we had a sink, and as soon as we had a sink, we gave back all of that slack. And when we have sinks everywhere, we're constantly giving back that slack. And so anytime we have part of our model where the host is slower, we're going to pay for it, as opposed to being able to just average it out. And if we, this is going to take a second to run, but when we open this up, what we're going to find is that this part, the host portion of forward backward, is going to get much smaller, and we're going to have a large CUDA sync on the end, which is essentially say you've scheduled all of your work, and now you can wait for the device to run. And then all of these pointwise operations, like, sure, it's not a bad thing to go grab something like apply rope and try and write a nice fused kernel for it. But it no longer becomes the highest priority because they're still pretty fast. And as long as you're more bound by these memory bound gems, then you can sort of focus there.
So Taylor, just a quick like time check.
Yeah.
So Google will kick us out from the Skull in about like 12 minutes.
Okay.
We can go back and continue in the Discord stage or the voice channel after for Q&A and what have you. But if there's sort of like any critical things that you want to screen share with, I would just like suggest sort of front loading that, and then we can go back and discuss more in Discord.
Yeah, so I think what I'll do is I'll just very quickly preview the two optimizations that I sort of didn't get to, and then just kind of describe how we got to them. So the first optimization that we can do is that we can go over, we're already doing gradient accumulation. And this is, again, another one of these cases where the task dictates the technique. Normally, I don't like gradient accumulation because it forces you to keep a bunch of extra memory because you have to have your gradients over the entire step. And that means you can't offset them between the peak of the activations at the end of the forward pass and the backward pass. But in this case, it's LoRa. Our gradients are tiny. We can do whatever we want. And we're already accumulating because we have such a tiny batch size. And so what we can do is we can essentially say, look at the shape of my tensor. And if I am in one of these rare cases where I have enormous tensors, just use a smaller local batch size. Just slice it up, do a non-accumulate or do an accumulating sub mini batch to just get past this. And it won't be great. I'm giving a batch, right? But it's not going to be great anyway because it's an enormous sequence length. This, by the way, is why we are also seeing some variability in the actual steps. But what this will do is this will prevent me from running out of memory and then use the batch size that I really want to use on the 90+% of steps. The other one that we can do, and this is, again, specific to Gemma. So if we look at the Gemma MLPs, where did they go? I think they're around here. Yeah. So we look at the MLPs, and what we see is that they actually have the same shape. And why not? Let's go look at the model. And what we see from the model here is it's a more structured MLP than, say, a Llama MLP. And these are the same shape. And so if we wanted to, we could actually concatenate the weights of these two and then slice off these two. And this would, again, by giving a larger map mall, especially when we go to larger batch where we're able to do more simultaneous compute and memory communication, what we find is that fusing these two together is only about 50% slower than an individual one. So it's not twice as slow. And so again, we can start to do this kind of thing. And what we find is that this becomes a very good candidate for now the kind of fused kernel authoring that we know and love. So yeah, I think that that's a pretty good place to stop.
Super cool. I mean, I really enjoy seeing someone who's like so proficient in like zooming in and out in this providing views. But one question is, could you maybe like share the commands that you normally use to do to run because that's if you like, for you it's like completely obvious and boring and so on, but if you someone like it's like started, it's like the first thing you need basically to know what options do you need to NCU and so on to get these things which are
important. I'll publish a studio that has among other things the notes and the commands that I'm running. But the other thing is, this is kind of why I'm working on integrating it into the Lightning platform, is a lot of this stuff is very mechanical, but very alien if you're not used to it. And so just being able to say, go that process or those groups of processes, just grab it and bring it back and like just handle the details and leave me alone, is tremendously useful, I think.
Yeah, definitely.
So
Mark, I don't know.
Thank you so much, Taylor. Like I think we can start heading out to the Discord channel. I guess like before we do, one of the reasons why I really appreciated this talk is like, for me personally, I only learned about how to do performance programming after seeing like a person like Will Feng at Facebook, who was like very used to doing this kinds of zooming in and zooming out, and that sort of gave me a lot of information and sort of what do performance people look for that wasn't available in the docs. So thank you, Taylor. I guess like now we have a recorded version of that experience. So I really appreciate that. Yeah, so folks, like start thinking of questions to Taylor. We'll head back, I believe, to the voice channel back in Discord, and we can just like hang out with Taylor for like another 15, 30 minutes and ask him any questions. Thank you, folks. And I'm seeing tons of emojis, so thank you so much, Taylor. I think people love this talk.
Thank you so much.
Thank you for having me. All right. See you in the Discord chat.